All right, we're going to look at piecewise functions, starting with some piecewise linear functions. So the example that we have to motivate this idea is an income tax table. Now this one is a few years out of date, I admit. It's changed a few times. The brackets have changed and the tax rates have changed, but it works pretty well for motivating the idea. So there's lots of ways to calculate your taxes, and most people probably don't do it from first principles. But if we say that we're starting with an income, let's just to be clear say this is really an adjusted gross income. So this is the amount that you're actually paying taxes on. We're not going to get into deductions and exemptions and all of that stuff. Okay, so just starting from an adjusted gross income, the way that we calculate our taxes really depends on how much money we made, right? If we make less than $6,000, then we're just paying 10%. It's very simple. Then if we make over $6,000, we pay a higher rate, 15%, but we don't pay it on all of the money. We still only pay 10% of the first 6,000, which is what this 600 represents. Then we pay 15% of the amount over 6,000. So if I look at the formula that corresponds to that down here in my table, this is what it looks like. We're paying 10% of that 6,000, that's the 600, plus 15% of the rest. That's where my x minus 6,000 comes in. As you can see, in order to know what formula to apply, you really have to know how much money you made. You can't just apply one formula to everything. But this function f of x is calculating the taxes due on an income X. So it is calculating one thing, and it is going to have just one output. It just has a whole bunch of different formulas, and you need to know what sort of bin your X falls into in order to know what formula to apply. So let's see how this works by calculating f of 68,000. Even if I don't know at all what this formula represents, I can see that the first step is to figure out where my 68,000 belongs in all of these bins. And I can see after examining these for a moment that 68,000 is in this one here between 63,550 and 132,600. I have to read this from right to left in order to really use it, right? I look on the right to figure out what bin I'm in, and then I read over to the left to figure out what formula I should apply. Once I've figured out what formula to apply, the way in which I apply it is the same as it would be if this weren't piecewise. I have a formula, I have a value of x, I'm going to just plug it in. So that's 13,708 plus 30% of, for my X, I'll go ahead and switch colors to that 68,000. And then back to black for the formula itself, minus 63,550. So this is something we want to calculate on a calculator. I think it's always best if we can get the calculator to store everything. So I'm going to start from inside the parentheses with my 68,000 minus 63,550. Whoops, accidentally hit the background. Then I will multiply that by 0.3, and then I will add that to 13,708 to get 15,043. So this is going to be 15,043. Note that, so it looks like the tax on $68,000 is $15,043. Note that I still just have one answer. This is really one function. It may be defined by 6 different formulas, but it's still one function. So one input, one output, right? Looking at this graph also helps us to see where we're going with the idea of graphing a piecewise function. If we want to estimate our 68,000, well, here's 70, so 68 is going to be right about here, right? If we trace up to this graph, that's right. Remember, we were just past the beginning of a tax bracket. That tax bracket started around 63,000. We're just a little bit past it, and we can see that the estimated tax is right around $15,000 from this graph. But we can see that the idea in graphing a piecewise function is just to graph each piece and make sure that those graphs don't extend beyond the x values for which they're defined. So this part that I just highlighted in purple is the formula that went with the 68,000, but notice that it stops, right? It doesn't continue on. This as a straight line would go on forever. We don't include that part of it. So the process of drawing a graph of a piecewise function includes all the details of graphing each piece and the process of restricting them to the appropriate domains. Notice we would call this a continuous piecewise function because the way the tax table is designed, these ends meet up. That's based on the fact that you don't pay the higher rate on all your money, you only pay it on the amount past the last tax bracket, right? So this is designed to make the endpoints meet up. This is a continuous graph. Since we are also familiar with constant functions, we can consider a piecewise constant function at this time. This represents the cost of making a phone call when roaming. So sometimes it costs a whole lot of money to use your phone if you're outside of your usual carrier. And the way this works generally is that there's a cost to just place the call and a cost per minute, but that if you talk for, say, 1 minute and 1 second, you are charged for 2 minutes, right? That there's a rate that applies if you go over 1 minute, but don't exceed 2 minutes, and that applies no matter where you are in that area between 1 and 2 minutes. And then if you manage to make your call last exactly 2 minutes, great. But if you go 1 second over, it just bumps you up to the 3-minute rate, right? So this is a piecewise constant function because within each interval, it doesn't matter what x is. The only thing x is really serving to do here is to determine which formula applies. There's no formula to actually plug x into. So if we want to evaluate f of 2.1, all we have to do is figure out that 2.1 is in this bin, that the formula is 3.38, and therefore our answer is 3.38, right? And therefore the cost of a 2.1 minute call is $3.38. We would say that this function is not continuous because it has breaks in the graph. So we would say no to this question. It's continuous if it looks like that income tax example that we looked at, where the pieces all meet up. If there's a single discontinuity, we call these discontinuities. If there's a single discontinuity, we would say that the whole thing is discontinuous. So we would call this piecewise constant only because each piece is a constant function. If it's part constant, part linear, we might just call it piecewise linear, right? In general, these are all linear functions that we're putting together.